feedback from the last lecture, which I'll quickly go through because it was quite interesting. So someone said, you were unhappy that I talked so much about philosophy and not so much about math. Well, I'll change that today. I'll talk about math, and then you're going to complain that there weren't any examples. The examples are coming on Thursday. They're just delayed. Someone else quite liked the philosophical perspective. This is one of the reasons why I show you this feedback, because there's often a diversity of opinions. Your samples from a distribution. Some of you like things that the others don't like. It's totally normal. It's fine, and I'll try and balance back and forth. Someone asked, can you please tell us more about what other methods to use other than Monte Carlo? I'll talk about this from Tuesday next week onwards. But the short answer is, you've already encountered one other method that's called the Laplace approximation. If you have a probability distribution, then you can find its mode and its curvature. That will give you an approximate posterior to use, a Gaussian posterior. That's one option. We'll encounter one more option called a variational bound. We'll do that Tuesday next week onwards. And then you'll have basically 3 classes of tools available: Monte Carlo methods, sampling methods, Laplace approximations, which are, if you like, differential geometric methods, if you want a grand word, local approximations, very fast, using just automatic differentiation, and variational bounds, which are actually a mixture of the two in some sense, and also something completely different in some other sense. Someone said sometimes it sounds like you're supposed to know some mathematical terms that we haven't actually heard before. So apologies if that's the case. I had the exact opposite experience. Last Thursday, I asked you who's heard of sampling methods, who's heard of random numbers, who's heard of Monte Carlo, and I would say 90% of the hands went up. And then I get the feeling that I should speed up a bit. And in fact, also, it looks like most of you thought it wasn't exactly fast, right? So if you're in that group, then either there is something else I don't understand about your comment, and then please write another one, or you might be in a small minority, and then that's unfortunately just to some degree bad luck. Because if I would go any slower, clearly the feedback shows then that I would be too slow. Finally, there were some good questions down here about stuff you didn't understand, that at least the first two have a lot to do probably with the person asking not having or not being able to remember their theory of CS undergraduate class. Might have been a long time ago, or maybe you didn't study CS. So the first question is, why do random numbers have to be countable? Any output of an algorithm always comes from a countable set. That's just how computers work, right? They use binary operations, so we cannot access the continuum. Turing machines produce countable outputs. Secondly, what's so special about the non-compressibility definition of randomness? Are there other non-computable properties of binary strings? So Rice's theorem says that almost all, well, actually all non-trivial semantic statements about algorithms are uncomputable. So a lot of things are uncomputable, not just randomness. And in fact, the results that I showed you, if you read them again, kind of show that there are a lot of random numbers. Most numbers are random, actually. Almost all strings are random strings, in a precise technical term for which I had a slide. So randomness is not a rare thing, but it's an untestable thing. It's something we cannot, an undecidable thing, something we cannot prove. We cannot look at a string and figure out whether it's random or not. And in fact, well, I think this is the, Kolmogorov's definition is probably the most precise one, also the oldest one, the most widely accepted one. That doesn't mean there aren't any others. If you go into more of a philosophical direction, there are various directions for other definitions of randomness that sometimes include Kolmogorov randomness as a special case and generalize on it, but that's then the domain of the philosophy of science, effectively. Maybe there'll occasionally be some other lecture courses coming up on the philosophy of science as part of the excellence cluster for machine learning and science, where this might come up again. And then there's a final point which gets me into the lecture for today, which was, it's a really a strong argument against using random number generators. Why? Why should I not use a standard random number generator in machine learning? My brief answer to summarize the message from last Thursday is, I'm not saying that you aren't allowed to use random numbers. In fact, I did use random numbers at some points over the lecture. What I did want to get across are 2 points. The first one is that there is a distinction between stochastic objects, random objects, and probabilistic concepts. And I hope that after this course, you're able to separate the two from each other and understand that randomness is not necessary to think about probability measures. Probability measures are deterministic objects. They are ways to distribute a mass of one across a space, and then you can manipulate those measures. That's what probability theory does. And that process has pretty much nothing to do with randomness. It's completely orthogonal to it. And this means it's possible to do things without random numbers. I'm not saying you're not allowed to use random numbers, but you should realize that there are often many other ways of doing a similar or analogous computation that completely do not use random numbers. And the word probabilistic does not mean random. So when someone, and you may occasionally encounter this in the future, conflates the two, then in your head you should say, there's something a bit mixed up here. Right? So a probabilistic method does not have to be random. A stochastic method is not necessarily a probabilistic method, and a probabilistic method doesn't have to be stochastic. And the other argument is that when someone argues for the use of random numbers in a computation on the basis of some supposed efficiency, based on this Cramer-Raoult bound type argument, right, that unbiased estimators can't be better than square root of n convergence, then I hope that you realize that this convergence argument is, in some sense, circular. It presupposes that you're using random numbers and then shows that using random numbers you can't be better than this rate. But there are other algorithms, or maybe other algorithms for your problem, that may be, in fact, incredibly more efficient. In some special cases, they might be exponentially fast rather than converge stochastically with the square root of the number of computations. And there is really no reason to not prefer those much, much more efficient algorithms. Just because they are biased, or because you can't even talk about biasness, doesn't rule them out. Because if you have an algorithm that converges within 20 steps in a biased way towards a perfect prediction in terms of machine precision, and compare it to an unbiased algorithm that takes 10 billion steps to get to that point, then it's much better to do those 20 biased steps and just arrive at the right answer. To conclude that part of my sermon from last Thursday, let me just show you some slides that I wanted to show you back then and didn't have time for, but I'll just now do them relatively quickly, just to point out again very explicitly how supposedly random numbers, which are not even computable, actually enter our computation. Because wherever we produce so-called random numbers produced from some distribution, what we actually do is we take standard, uniform, quasi-random numbers and then somehow translate them. The basic example is the way to draw from a Gaussian distribution. So here's the algorithm, one of the, or maybe like at least the textbook algorithm for drawing from a Gaussian distribution. So the method that you get when you call, well, I mean, that's not actually the algorithm you call, but sort of what you can think of as the algorithm you call as jax.random.normal, standard normal. Here's the method. There's not much point in looking at it. You can see that it's a short piece of code. It's better to look at a visualization. Here's a picture from Wikipedia. Here's how the algorithm works. You draw two uniform random numbers. So there's a box here of length 1. You pick a random point within that box, and then that point gets translated in a deterministic fashion, non-random fashion, into something that can come from a Gaussian distribution. And if you move around, you can see that by moving up and down, we are changing the scale. It's a bit difficult to see. And if by moving left and right, we're changing left and right is the scale, up and down is the angle. Now you see it better. Over here it's easier to see, right? So, difficult to get my mouse so tiny. So the up and down gives the angle on the circle, the left and right gives the radius. And then there's a cool trick that you only actually need one random bit to produce, one uniform random number to produce a new independent sample. And so you can sort of interleave these and use this random number from step t as this random number from step t plus 1. And so that every time you want to create a new standard Gaussian random number, you only ever need one new standard uniform random number. So this is an algorithm called the Box-Müller transform. You can remember the name Box. He might show up again next Tuesday. He did other things as well. That's not actually the algorithm that is now used in practice. George Marsalia, the guy with the CD I told you about on Thursday, came up with other algorithms, including the one that I think is currently still in use. It's the last one, the so-called ziggurat algorithm. A ziggurat is this Mesopotamian style pyramid, right, with the steps. And so he came up with a cool way of using rejection sampling. We'll talk about rejection sampling in 15 minutes to build a very refined, quick algorithm that very efficiently produces standard Gaussian random numbers. It's very difficult to understand. It's a sort of a nasty kind of difficult to look at code. But the point is, the way to produce standard Gaussian random numbers is to plug into a random number generator that produces standard binary bits, translate those binary bits into supposedly random binary bits into a uniform random number by reading out a floating point number, translating them into a floating point number, then translating those into Gaussian random numbers. Now we have standard Gaussian distributed random numbers. So we're still sort of harking back all the way to this random number generator. And now how do we get to non-standard Gaussian random variables? Does someone know? We've done this in passing. If you have a draw from a Gaussian with zero mean and standard deviation 1, how do you get to non-zero mean and non-standard covariance? Yes, it's just scaling. It's the answer. So we scale by the covariance, actually the square root of the covariance, and then we shift. Here's the idea for this. You may have seen that I did this in my code. There are two different ways of doing this. One uses the singular value decomposition of the covariance. Actually, there are at least two. I mean, there are even more. Basically, what you need is you need a matrix square root of the covariance and then the mean. There are various matrix square roots. They are not uniquely defined. The singular value decomposition of the covariance provides a matrix square root. And then what we do is we take our standard Gaussian random numbers. So these gray dots are supposedly random draws from a standard Gaussian. Then we scale by the covariance, the square root of the covariance. So these two steps here were multiplying with first in green the singular values, so to scale the covariances in the right directions, and then to rotate by the singular vectors. And then we add the mean. And now we have a draw from this non-trivial, non-standard Gaussian distribution. You can do the exact well, there's another way of doing this, which doesn't use the singular value decomposition, but the Cholesky decomposition, which we also encountered. You remember the Cholesky is somehow cheaper to compute than the singular value decomposition. It's like a third of the cost. It uses symmetry more efficiently. It's less numerically stable, but because it presupposes some things, positive definiteness, for example. But you speed up by a factor of 3. It also provides a matrix square root, but it actually amounts to a different transformation that does something else to get from the gray dots to the final distribution. And you can go back and forth in these slides if you like, and you'll be able to convince yourself that these red dots are different from these red dots, but they start with the same set of gray dots. They just end up with different samples. And that's a typical aspect of these sort of ways to produce random numbers, that in distribution they do the same thing. They are effectively draws from a standard Gaussian distribution. But depending on how you do it, you end up with different numbers. And so sometimes you have to be really careful when you write code and you think you're going to be writing it in some kind of reproducible manner, that minor changes to the way you operate on random numbers can lead to non-trivial changes in the output of your code. So what this mostly, again, is trying to stress, just say again, is that the use of random numbers is completely post hoc to probabilistic inference. You can write down a posterior, a prior, and a likelihood, and their product without using random numbers. Drawing from a Gaussian process, this is actually something I guess Marvin told you in his tutorial, is you can think of a draw from a Gaussian process as some kind of second-order function where you first define a space of functions that is addressable through the mean function and the covariance kernel of the Gaussian process. And then what you're left with is an object that takes in random bits and translates them into random samples. And that, just like you can first create the random samples and then instantiate the Gaussian process on its inputs, you can also do this currying the other way around and say, I first instantiate my probabilistic process, or stochastic process called Gaussian process, with a mean function and a covariance, and then afterwards I have a data structure that can take in randomness and produce random samples. In fact, pretty much any and all random numbers that we produce in machine learning are of this fashion, not just Gaussians. What's the standard way of producing a random sample from a general probability distribution? Since some of you have taken statistics classes before. In an analytic fashion, not in an approximate fashion? Yes, so it's the inverse transform of a cumulative density function. I have one slide for this. So if you want to draw from some general probability distribution P, then technically one way to do this is to compute the cumulative density function. Let's assume for the moment that our problem is univariate. Then the cumulative density function is uniquely definable as this function that is the integral over the density if it exists from minus infinity to x. Then that's a number between 0 and 1. So if we now take random numbers on, and it's a monotonic function, right? It's a monotonic function that maps from minus infinity so from the real numbers here, from the continuum to 0, 1. So it has a unique inverse. And that inverse maps from the 0, 1 simplex back into the domain. And if you now draw randomly from the 0, 1 simplex and then use this backward transformation, you get samples from the true distribution. Here's an example for this for the exponential distribution. That's my very basic exponential family, actually, parameterized by some length scale lambda. So this function is easy to integrate on a piece of paper. I do this here, right? So the integral over this function over its domain, so this thing is only defined from 0 to infinity on the positive numbers. Then you get this object, right? So the integral over 1 over lambda e to the minus x over lambda is 1 minus e to the minus x over lambda. Now we can try to compute the inverse of this if we draw standard uniform random numbers. It's actually, you can make your life a bit easier by drawing not a uniform random number, but 1 minus a uniform random number. That's still a uniform random number, but it gets you an extra 1 minus, so we can easily cancel out things. And you'll find that you just have to set x to minus lambda times log u, and that's a way of drawing from this distribution. In fact, that's the standard way of drawing from exponential distributions. You just take standard uniform random numbers and then map them through this inverse, which I've tried to do in this picture here. So in red, you see the probability density function. In black, the cumulative density function. And then what I've done here is I've drawn uniform random numbers on the y-axis, computed their inverses using this black line, and then basically found corresponding x values. And to visualize that they are actually standard draws from this distribution, I've now also drawn uniform random numbers between 0 and the height of the red curve and plotted them at this arbitrary height, which gives us a sort of, you can see that there's roughly a uniform distribution of these red dots under the curve. And that's a sort of a visual proof that they are draws from this distribution. If you do this in multi-dimensions, then you just use the product rule. So you just keep going one dimension after the other with the cumulative density function, and then you get the correct output. So these are all analytic ways of producing random numbers. And maybe in a sense they are a bit boring because they provide like base case functionality. So if you use scipy.stats and look at their probability distributions that are encoded there, the basic standard distributions, typically exponential family distributions, then the algorithms used to produce random numbers from those distributions tend to be of this nature, or at least of an approximation of this nature. But there is more general classes of problems where we don't always have access to the correct, certainly not necessarily the cumulative density function of the distribution. And the rest of today's lecture will be about algorithms that are designed to work in this setting. And here I should maybe have made a slide for this. Let me see if I can do this without a slide. If you're wondering why we need to talk about these methods, maybe there's some kind of hierarchy of how complicated an inference problem is, or a problem of drawing samples. In the most elementary case, you have a parametric form of the probability that even allows you to compute the cumulative density function. That's, for example, true for Gaussians, for basic exponential family distributions like the exponential distribution, the Dirichlet distribution, and so on. And for those, there are these standard methods that produce samples from these distributions. And they're basically our way in. I mean, they're already one layer above, right? So that the most basic functionality is just to produce random bits. That's what we talked about last Thursday. And now getting these standard samples is all deterministic transformations of these random bits. So now the next more complicated thing might be a setting where you have a probability density function, but you don't have its cumulative density function. Because the cumulative density is an integral, a partial integral, over the PDF, and integrals are hard, so you might not be able to compute it. That's still not the most general case, right? There'll be more general cases, but a typical setting may be that you have this probability density function. Maybe you have it up to a normalization constant. And why might you have that? Because you might have written down something like a prior times a likelihood. Those two things you know we can talk about, right? The prior you get to choose, the likelihood you can motivate from some statements about your data. And now what you're interested in is the posterior over x given y. There's two problems. The first one is that you need actually a normalization constant, right? So you would need something like an integral over this thing, which you may not have, might be hard to do. And then, even worse, this thing may not have an analytic form that allows you to compute a cumulative density function. For this setting, there are algorithms available called Markov chain Monte Carlo, or just more generally Monte Carlo methods, which we'll talk about now for the next, well, 1 hour, basically. And then there's one layer above that, where even this object, this distribution is unknown. All you get is samples from it. And that's the setting we typically have in modern generative models, so we'll talk about that on Thursday. So what I'll do now is maybe a standard textbook style introduction to increasingly elaborate Monte Carlo methods. And I'm wondering to which degree you've heard about these before and when you'll get bored or when I suddenly jump over you. So who's heard of rejection sampling? Oh, not so many. Cool. Great. So then the rest of you gets to be introduced to rejection sampling today. That's one of the most basic Monte Carlo method. It was invented actually very, very long time ago already, 17-something, by Georges-Louis Leclerc de Comte de Buffon. And it works. It's so easy to think about that I can just show you a picture. And then you can immediately see how it works and why it doesn't perfectly work well. So the idea is, let's say you want to draw from such an unnormalized distribution. So the assumption is you have a setting where you get to write down your prior, you know what the likelihood is, you don't know the normalization constant, you just know these two terms. But you can encode these. These are functions you can write down in your code. Then what you do is, so this is this black curve here, this thing. Now what you do is you find another distribution that you know how to draw from. This red thing is supposed to be a Gaussian. And you find some number c such that you know that c times this distribution that you draw from, let's call this distribution Q. Q is always the nomenclature for the approximate thing, and P for the correct thing. Let's say you found a C somehow such that C times Q of x as a function is an upper bound to this unnormalized probability density. So here, this red curve is always above the black curve. And now what you do is you draw from this distribution Q, so for example from this Gaussian. These are these gray dots in the background that you see. These are all standard Gaussian draws. And now every time you draw such a location in the X space, so that's actually a location somewhere here, what you do is you additionally draw a standard uniform, I keep saying standard, a uniform random number, scale it by C times Q. So let's say we have randomly drawn a point here. Now we compute a uniform random number and scale it by the red number above. That gives us a uniform point between 0 and the red line. Then we check whether this uniform number is above or below the black line. If it's above, we just forget about this sample. We just throw it away. We never touch it again. And if it's below, we keep it. So this is visually what's happening here, right? I've drawn every point on this plot. For every point, I check whether it's above or below the black line. When it's below, I keep it. Those are the black dots. When it's above, I throw it away. Those are the gray dots. And what I'm left with, this is the visual proof, is clearly uniform random samples from the area underneath the black curve, which correspond to, if you just read out the x values, to IID samples from the black curve. So this is a so-called direct, or sometimes called simple Monte Carlo method that directly draws samples from the distribution. There's a question. How do you find the number C? So that's the first problem. We need to find some upper bound. And that's not always possible. And if that's the case, then you can't use this method. We'll get to that in 2 slides. So there's a trick to move on forward from that, yeah? That's a good question. Actually, I don't know. Read up. This is the sort of history thing that I haven't checked before, so I don't know. I just have to say, I don't know. Okay, good. So this is one problem with this approach, is that you need to know this upper bound. Actually, there's another one, which is that it really only works in low-dimensional problems. Can you imagine why? Yeah, so you're saying the right thing, but it's not really like the answer, right? You're saying there's a curse of dimensionality, and that's true. So the problem is that this volume here of stuff that you have to throw away may scale very badly with dimensionality. So here's an example, a nice argument from David Mackay's book. I forgot to put, no, actually there's the citation up there. I just forgot to make it a link. So let's imagine, just for the sake of argument, we wanted to draw from a Gaussian distribution, P, using another Gaussian distribution, Q, as the proposal distribution. Obviously, you don't need to do that, but it's a good exercise to think about how to do this. Then the value of the constant here, this upper bound, can be found analytically, right? It's just a relative height of the Gaussians at their mode, so that we are always above. And because Gaussians have this closed form normalization constant, we just write down what this relative value is. So we find that our constant that we need to multiply by is the relative value of the standard deviations raised to the dimensionality of the problem. Because that's how D enters in the normalization constant of a Gaussian. And that means we need to increase D, we need to increase C exponentially with the dimensionality of the problem. And the acceptance rate, so the rate of the volume below here and there, drops like 1 over C. And so therefore, this drops like 1 over something that's exponential in the dimensionality. And so very quickly, we'll reject most of the samples. So in a 100-dimensional problem, for example, even if the relative error between the proposal distribution and the actual distribution you want to draw from is just 1.1, you'll accept basically every 10,000th sample. And so that's going to be the rate that enters into our square root convergence in terms of compute, right? So we'll get a Monte Carlo estimate that in terms of the actual samples we draw converges like the square root of the number of samples. So that already tells you how many samples you have to draw. And then you have to multiply that number of samples by this rejection rate, by 10 to the 4, for example. So that's a hugely inefficient algorithm then. So the next step, you can now do this rapid, we can go through the centuries really rapidly. The next thing people came up with was exactly an answer to both of these problems. Also to your how do I find C, the upper bound. The next idea was something called importance sampling. Again, hands up, who has heard of importance sampling? Does the number go up or down? Seems like it's the same set of people. Okay, so importance sampling is a method of doing basically the same thing as rejection sampling, but without rejecting. You keep all the samples and you reweigh them. So the idea is the following. Here's a nice short argument. Remember that what we're trying to do is to compute an expected value, something like this, by drawing from P. Now, let's say we can't draw from P, but we can draw from Q. We have another distribution that we can draw from, and we can draw random numbers from Q. Then what we can do is we draw from Q, and every time we draw from Q, we compute this ratio P over Q. We can do that because we have access to Q, obviously, because we can sample from it, so we can surely evaluate its probability density function. And we assume that we can evaluate the probability density function of P. Let's assume for a moment that we can actually compute the value of P exactly. It turns out you don't even need to know the normalization constant. Then we can compute this value, this ratio P over Q. That's called the weight, the importance of the sample, the importance weight, and multiply the value of F at that point with this weight. And now, clearly, when we compute the expected value of this, just in terms of this equation, we're computing the expected value of this under Q, which is equal to this thing, which is equal to the thing we're trying to compute. So it's an unbiased estimate of the object we're trying to compute. Nice. Right? And now we don't need an upper bound. We can just use an arbitrary proposal distribution. And in fact, we can even get away with not knowing the normalization constant of P. So if we only know P up to a normalization constant, then we can actually estimate this normalization constant as we go by summing up importance weights effectively. So that's still, well, if we do that, by the way, this problem creates a bias, so then it's not an unbiased estimator anymore. But I already said, whatever, we don't care so much about biasness anyway. But if you have a normalized access to P, then you can do this in an unbiased fashion. So of those of you who've raised your hands, does someone remember what the problem with this approach is? Even if you didn't raise your hands, you can look at this equation up there and wonder where the argumentative catch might be in this statement. The problem with this normalization constant, I mean, there is this problem that this is a bias, this makes the estimate biased. But this is even a problem if you know the normalization constant. There's something else. Yes? Good point. So we are dividing by Q of x, so we need to make sure we're not accidentally dividing by 0. Very much computer science answer. Perfect. Yeah, so that's true. You need to make sure that your proposal distribution has support wherever the correct P is. And that actually is it's also a hint for like a more general version of the same problem. So not only do we have to make sure that this Q has to have non-zero value wherever we sample, but actually let's think about what happens if Q has a non-zero value, but it's a really tiny value. What then happens is, of course, that number gets very large, right? P over Q. And therefore this weight gets very large. And so the problem with this is going to be, like, let's think back to what we did on Thursday. What's the variance of a Monte Carlo estimate? Right? We said that simple Monte Carlo produces unbiased estimates. What's the variance of this unbiased estimate? Yes, it's the variance of the function that we're trying to estimate divided by the number of samples. And that divided by the number of samples gave us the square root weight convergence, right? But this variance of F is now replaced with the variance of this thing, f times p over q, right? Because we're now actually estimating that. And that might have much, much higher variance, actually. So here's a little picture that, unfortunately, is a bit maybe too high level, difficult to look at, too many things plotted. It's an old plot. But what I'm showing here is in black, there's some distribution, right? I've made up a weird distribution in black. And in red, there's a proposal distribution. So let's say someone gives you this black distribution and says, please sample from it using importance sampling. Then you will say, OK, I'm going to use this red proposal distribution. It's a Gaussian, so it has support everywhere, right? So it's not a problem with divide by 0. But it has very low probability in this region here. So what's going to happen? So, I mean, there's two ways to think about this. One of them is that the variance of this distribution that is given by, so let's say we want to compute the mean. The mean is this expected value of this linear function here. Then we're actually computing the expected value of linear function times the ratio between red and black. That's this golden function here. That has a much, much higher variance. And therefore, it'll have a much lower convergence. Another way of thinking about this, maybe less from the perspective of a mathematical quantity and more from an algorithmic one, is I'm going to draw these red dots. And most of the time, I'll get something from the center of this Gaussian, and that'll have a relatively low importance weight. Right? I'll keep finding out that the black curve is below the red curve, and therefore, this is an unimportant sample, unimportant sample, unimportant sample. And then very, very rarely, I'll get something from the tail over here. And whenever that happens, I get a huge importance weight, which will completely shift my estimate around. And then I'll have to wait for another long time to get the next interesting sample. And this is actually the nastiest aspect of this importance sampling idea, that if you think about this from this algorithmic picture, that you may not even notice that it's a problem. That's something that happens with importance sampling, is that you keep drawing from your proposal distribution, you keep getting small weights, and you think, oh, it's all good, I have very low importance, everything is fine, low variance estimate. If you keep a running estimate of the variance of the samples, it'll be low, right, and everything will look good. And then every 10 million samples, something will come in with a weight of 100 million. And then everything blows up, and you'll get one huge jump in your estimate, and then you'll discover that something is wrong. Or maybe you don't even. There are adversarial examples that can be constructed. There's one example in David Mackay's book, where the variance is actually unbounded. The estimate doesn't have a variance. It's not defined. And yet, when you run the algorithm at finite time, you always have a finite variance. And so you always seem to be convinced that everything is fine. And you never notice that you're actually sampling from something that doesn't have a variance. OK, so all of these are basic algorithms for drawing from probability distributions that you know up to normalization constant, and they have problems that mean that they typically don't work in high-dimensional spaces. And so there is another class of algorithms that I'll talk about after the break that arose in the 1950s, historically largely out of the Manhattan program in the US, by various people who have taken out all the pictures, had to do complicated computations about expected values of some densities of particles flowing around in a roughly spherical volume, getting scattered all the time, trying to find geometry such that the whole thing would explode as a nuclear bomb. And they are called Markov chain Monte Carlo methods, sequential methods for producing samples from a general probability distribution. After the break, I'll tell you how they work. Before the break, I can maybe briefly tell you that they are connected with the names of many different people, and the history is often a bit murky. It's kind of known roughly who was involved in inventing them, but it isn't really clear who did what part of the work, partly because the people involved in them were in a secretive lab somewhere in Los Alamos, and they didn't necessarily publish papers in open source journals, and only like 40, 50 years later or 30 years later at some conferences, they tried to claim fame for some of these methods. So these methods work by producing a sequence of random numbers such that the sequence as a whole, asymptotically, when you randomly scramble it, can be thought of as independent samples from the distribution. But locally, from one step to the next, they actually keep dependence between the samples in a Markovian style fashion. So you use the local estimate, the local current draw to produce the next draw. How exactly that works, I'll tell you after the break. Let's meet again in 5 minutes. Who has heard of Markov chain Monte Carlo methods, MCMC? It's interestingly, it's not entirely the same set of people who have heard of rejection sampling and importance sampling. So that's interesting. So for those who didn't raise their hand, here's the basic structure of these algorithms. There is an elementary algorithm called the Metropolis-Hastings method, even though that's probably a misnomer, that works as follows. So let's first start with an analogy. Let's imagine I wanted to solve an optimization problem using random numbers. That's not what I want to do, but it's a good way in. So let's say I wanted to solve a maximization problem. I'm given some unnormalized probability distribution P, and I would like to find the mode of that distribution. One, admittedly very inefficient way of doing that is to say I'm going to use some proposal distribution Q, which is a conditional distribution that has something to do with a local current estimate xt. That's where the Markov structure comes in. So I'll produce a sequence of xt's, and at every time t, I will use this kind of distribution. This could, for example, be a Gaussian distribution around xt. So xt is the mean of the Gaussian, and x prime is my new random sample. Could be some other distribution, but let's say a Gaussian, that's a typical choice. Then what I'll do is I'll draw a random number from that standard distribution, from this proposal distribution. Let's say it's a Gaussian. And then at this location that I've drawn, I'll evaluate this ratio of my target distribution at the proposed point to the target distribution at the current location xt. If that number is larger than 1, then that means the new proposal has a higher probability than the older one. And I'll just take that, right? And I'll make a step in that direction. I'll update my Markov chain. I'll keep going. And if that new number is not larger, then I'll just stay where I am, right? Then you can maybe convince yourself, or I hope you'll be convinced, that if I run this for a long time, this algorithm will converge towards some local maximum of the distribution, right? Because whenever it accepts, it goes uphill. And it'll keep accepting until it can't go further uphill, and then it'll just stay forever where it is. So the Metropolis-Hastings algorithm is very similar. It's just that you can imagine that if you want to sample, you can't only accept things that go uphill. You sometimes, with a certain probability, also have to go downhill so that you can move around in the distribution. And this algorithm is all about figuring out the right ratio of probabilities to go downhill such that asymptotically you actually draw from the correct distribution. And it's a minor change, actually, to this algorithm. The basic idea is we're just going to accept with a probability that is given by A. If A is larger than 1, we just clamp it at 1. If it's less than 1, we just accept with that probability. That's it. And then there is a minor generalization that was already in the original distribution, at the original paper. If you assume that you use this proposal distribution in general, you have to sort of correct this A a little bit. Here's the corresponding statement. So the algorithm works as follows. We draw from the proposal distribution, then we compute this A, this ratio between the probability at the proposed point divided by the probability to go to the proposed point, given that we're at the current point, times or divided by the corresponding rate at the current location. And then we accept with probability given by that number. If that number is larger than 1, we always accept. If the probability is less than 1, we accept with that probability. And if we don't accept, then we add the number that we just draw to our list of samples. We don't throw it away. We memorize it in our Markov chain. Now there's one simplification that's typical is that if you choose your proposal distribution such that it's symmetric, so that an exchange between xt and x prime does not change anything, that's the case for Gaussians, right, because they're symmetric around the mean, then you can actually cancel out these two parts here, and you just stay with this ratio that we've seen before. So there's a really nice visualization of this by a guy called Qifeng Li, and I've been using his visualization for I don't know how many years. because it's a great way, it's much better than any plot that I could possibly make. Here is this algorithm running, random walk Metropolis-Hastings. And what you see in the background is, so I recommend playing with this cool tool, it's very nice. What you see in the background is a probability distribution that we'd like to sample from. The black dots are samples. And what you see here is the Markov chain moving. So at every point in time, you see that there is this proposal distribution, that's this circular Gaussian around the current location. And then the algorithm makes a proposal, so it draws from this distribution. And then it evaluates this ratio A between the new probability and the old probability. When the ratio is below, then you see a red line, and it rejects. It just stays where it is. It adds another point to the list. And then you sometimes see that you get some points that are very dark. Those are because all the samples stay in the list, right? So they are returned as samples. And when the ratio is such that the sample gets accepted, you get a green line, and then the algorithm steps and makes a step. And we can now, we can speed this up. There is some cool way of speeding this up, and now you see the algorithm, moving around, drawing samples, and you see that it's moving, right? And it moves across this region. And one first thing to see, that's, oops, let me see if I can slow it down again. No, I can't, but I can just reload. So, that's the wrong method. Let's see, can I go back to random walk Metropolis-Hastings? So here we go. So the first thing to notice is that this is clearly a Markov chain. So you can see that if you take just any 5 steps out of this chain, then these are not independent samples from the full distribution. The algorithm will be local somewhere, it moves around. But if you zoom out and let this thing run for a long time, and then look at the density of the samples that are being produced, you can think of them as IID samples. The second thing you may notice is that clearly the shape of this proposal distribution will matter. If I make this proposal distribution too wide, if I use a very large distribution, then you can see that most of the samples get rejected. Most of the time, this huge Gaussian will propose samples that are way outside of the typical range, and I'll get a lot of red lines, and then the method will barely take a step every now and then. And so it'll get stuck for a long time. That's not a good choice. If I make the proposal distribution very narrow, now we're here, then I get this super tiny distribution that can only make tiny steps, and those steps are random, so it'll do a random walk, and then will only make progress very, very, very slowly. So there is some optimal choice to be found here. It's probably something like this, where the algorithm accepts often, but also then makes big steps when it accepts. And that's actually a problem with Metropolis-Hastings, with the standard way that this standard implementation. And now we'll talk about how to fix that. But first, I need to convince you that this is actually a valid way of producing random samples. And it's actually quite instructive to see the proof for why this produces asymptotically IID samples from the distribution. It's a 2-step argument. And both of these steps they are not actually that interesting from a technical perspective of how the proof works, but they're interesting from the perspective of why someone would argue this way. Or, basically they're interesting from the way the proof works, not from actually the numbers that go into the proof. So the standard way to show that this Metropolis-Hastings method, which by the way was probably not invented by either Metropolis or Hastings, the historical idea seems to be that Metropolis just provided some compute, and actually the method was invented by probably these 4 people who are just at the end of the paper because they have surnames starting with R and T. These are both couples. This is the husband and wife Rosenbluth, American statisticians, and Mitzi Teller and Edward Teller, who I probably don't have to introduce, right? So some of the father of the nuclear bomb, supposedly, and his wife. Both migrants, by the way, from Hungary, who had to leave Europe during the Second World War. I might get back to Teller later. So how does this work? So the standard way to show that this algorithm works is using a actually not necessary but sufficient property of a valid Markov chain Monte Carlo method called detailed balance. Detailed balance is a property that is used for the proof, and it looks like this. you show that the probability to be at some location for this algorithm and then transition to so actually the target distribution times the probability for the algorithm to transition to a new point x prime if it is at location x is equal to the target distribution at x prime and the probability to step the other direction. One can show that this is the case by just writing into the equation what the probability is to move from one point to the next under the Metropolis-Hastings rule. So here you see this transition probability, right? This is basically this A from my previous slide. So we just, it's just algebra. You just move things around and you see that they are the same thing. And now, if this property holds, which is called detailed balance, then one can show that a Markov chain that has this property has at least one stationary distribution, where stationary distribution means this thing down here. So if you assume that you have samples, if you have a set of samples that are drawn from P, then that set of samples is invariant under the action of the algorithm. So if you take such a set of samples, let's assume you have a very, very large number of samples, they come from P, and we apply the rules of transition of the algorithm, then we get samples from P again. Right? So the set of samples after the transition of the algorithm comes from the same distribution as before, and that distribution is the target distribution. So that's at least one. And now there is the other direction, which is we need to show that there is at most one stationary distribution, namely P, and then we know that the algorithm works because it draws at most from P and at least from P. Right? So there can only be one distribution to draw from. And that other argument goes by a fancy philosophical concept called ergodicity. Ergodicity means that a sequence is aperiodic, it contains no recurring sequence, and it has positive recurrence. So if you are at some location, then there is a probability to come back to that location in the future. So actually, this is such a nice sort of mathematical definition, but really it's just the definition of randomness again in disguise. It's just like a rewriting of what we mean by a random sequence. One aspect or actually it's a subset of the properties of random sequences, that they have no recurring subsequences. So basically this proof says, if you have a way to produce random numbers, and we know that there is no way to produce random numbers, but if you had a way to produce random numbers, then this method would work. Now in reality, we only use some approximation of that. We use a pseudo-random number generator, which of course has a recurring sequence, but it's just so large that we pretend it doesn't exist. And then we can use this proof with a bit of hand waving, and we'll find that we have an actual algorithm that produces asymptotically samples from the true distribution. However, this is again just a statement about asymptotic behavior, not a finite time statement. It doesn't say after 100 samples you have something that is IID, right? And in fact, the scale on which these algorithms produce independent samples, you can sort of visually think of from this picture. Right? You can think about how long does it take for this process to basically move once from one corner of this distribution to the other. That's the typical time scale. And then that's the rate that we have to multiply by, that we have to think of in terms of square root of that number of steps. That's going to be the convergence. Right? On that length scale, things are independent of each other. Another way of sort of making this a little bit more precise is due to David Mackay from his book, where he sort of has a rule of thumb for this. He says you can think about this problem. So here's a picture of Metropolis-Hastings drawing from a Gaussian. In red are actual samples from a Gaussian, standard samples, and in blue is the same number of samples from Metropolis-Hastings. So his argument goes, if you're drawing from a high-dimensional space, which you typically do, right? If it's a low-dimensional space, you might as well use importance sampling or whatever, or actually just use an integration method because they converge much faster. But in a high-dimensional space, you'll typically have to choose a proposal distribution Q, which will be somehow isotropic because you don't know much about your distribution, with a scale. So the width of our Gaussian proposal distribution will probably have to be something set to the order of the smallest length scale of the problem. Because in high dimensions, most directions are empty, right? So in this picture here, you can see that there's basically one dimension along which the problem has its extension, and then in the other direction, it's pretty much empty. So to make sure that that proposals get accepted, we typically have to set the proposal distribution to the short length scale. In this case, the short length scale is this eigenvalue of the corresponding covariance matrix. And then that means our typical step that the algorithm takes is something of length, short length scale. And in all the other directions, it'll do a random walk. Just like in this picture I just showed you in this visualization. So to make progress in the long direction, along here, we'll have to wait a time that is proportional to the short scale times the acceptance rate, and then the square root of the number of time steps, because it's a random walk, right? And random walks move a distance that is proportional to the square root of the number of time steps. Brownian motion, we've talked about it when we did Gaussian processes. Now you can solve for t, and you can say, to create one independent sample, we have to rearrange everything. You have to typically wait a number of time steps that is quadratic in the ratio between the longest and the shortest time scale. So the longest and the shortest time scale, if you think of a covariance of the entire distribution, you can think of as like the condition number of the covariance, right? The ratio between the largest and the smallest eigenvalue. And then you have to square that, so it gives you a very bad rate typically. And in fact, here's an example of drawing from, I actually forgot what distribution. No, it's this Gaussian distribution. It's this picture here. Yeah? And in red, you see the convergence rate of a bunch of exact samples. So those are square root of the number of samples. And in blue, you see this Markov chain Monte Carlo method that converges very slowly. So a problem with these methods is that they have these free length scales that they have to walk on and take a random walk. And actually, it can be difficult in practice to detect this, because if you think about this, like imagine you're inside of this method moving around. How do you check whether you've covered the entire range? It's very difficult to do because you don't have this picture, right? You can't see what the length scale of this grayish distribution in the background is. You're just sitting inside of this spaceship moving around here, and nobody is telling you where the mass is. And you might be stuck in some tail of the distribution, and everything around you, so let's say, I'll make a version of this again. Sorry. You can already see that there are, of course, smarter methods that work better. So let's say you're in this thing. Oh, that's the probability. I don't mean that. I mean, it's wrong. I wanted random walk MC. So here we go. So if you're inside of, if you're in this situation, then everything around you looks good, and you'll just accept. So you think you're doing fine, but in fact you're not. You're completely stuck. And so it's difficult to sort of detect the difference between a method that just is actually accepting properly most of the time and a method that is stuck in some region. So basically, a lot of research has gone into this over the years from like 1950 to the early 2000s to produce smarter algorithms that somehow fight against this random walk behavior of this basic method. And a lot of smart people have invested a lot of time, and I'll show you 2 examples of how to make this faster. But first, there's a question. Yes, so you're raising a good point about the acceptance rate, right? You want to make your acceptance rate, well, you can watch the acceptance rate basically as the method runs. One way to bug fix such methods is to watch the acceptance rate and to say, I want something that's on the order of 1/2, right? If the acceptance rate is 1, then I'm certainly stuck in a tiny region. I just accept everything. If the acceptance rate is 0, then then my proposal distribution is way too wide. So I can look for something like 1/2, but that's only a partial answer, right? It doesn't actually fix this. So here the acceptance rate is probably a little bit. It's not quite 1/2. Let's maybe make it a bit wider. So now we probably get closer to 1/2, and we're still effectively stuck. Right? So now what people then do is they have additional well, when this was the standard algorithm, there are other diagnostic tools. For example, you can measure the autocorrelation between of these samples. And you check how quickly they become independent of each other across the chain. And that's one way of finding certain types of errors, but not all of them. You can also still be stuck. So, for example, this chain here has autocorrelation pretty much 0. It produces pretty much independent samples, but it's still stuck. So bug fixing, these kind of tools at least used to be very difficult. Now it's gotten a little bit better, but also these methods have increasingly been superseded by the stuff we'll talk about on Thursday. Okay, so maybe, by the way, just to point out, because of the structure of this acceptance rate, any normalization constant cancels out. So you can directly apply these methods to unnormalized distributions. That's very nice. Oh, and one thing I have to tell you, yeah, so this is the first algorithm that maybe improves on things that I need to mention because it's in the homework for this week. It's a variant of this algorithm, and it's called Gibbs sampling, named after Maynard Gibbs, who worked on thermodynamics. And it uses the following idea. So this is a bit of nasty math, but actually, it's one of these algorithms that are very difficult to write down and then very easy to implement. The idea is the following. We make a specific choice in this Metropolis-Hastings chain where we choose the proposal distribution Q to be conditional distributions in a sequence of a subset of the variables. So this is difficult to write down in math. So I'm just going to wave my hands about and tell you how this works. And then it's much easier to think about it mentally, verbally, than to write down equations. What we do is, let's say we're sampling from a 10-dimensional problem. Or in fact, in your homework, you're going to be sampling from an 8-dimensional problem. There'll be 7 special dimensions, and then there'll be an 8th other special dimension. Or there's one set of 7 dimensions and one set of an 8th dimension. And sometimes, when you do Bayesian inference, you get lucky and you get an interesting structure where the conditional distribution of one subset of the variables, when conditioned on the other, is a closed form expression that you know how to sample from. And then vice versa, the conditional distribution of the complement, given the initial subset, is also closed form. In your homework this week, you'll discover that there's one variable that you're interested in, ultimately, and then there are 7 annoying variables that you have to deal with. And it turns out that those 7 variables are easy to draw if you know the 8th variable, and the 8th variable is easy to draw if you know the 7 variables. And then Gibbs says, here's what you do. You just iterate between holding one variable fixed, resampling the other ones, then holding those fixed, resampling the other variable. And then you just keep going back and forth. And that's actually an instance of this method. It's an instance where the proposal distribution is given by a conditional distribution that says, let's keep some subset fixed and redraw the other ones. And then when you do that, you can plug in this update proposal into this acceptance rate equation for Metropolis-Hastings. Everything cancels out, and you'll find that the acceptance rate is 1. So you'll just always accept, which means you don't even have to think about accepting. You just run the algorithm. And this is not in general a good idea, but in these settings where you have this conditional analytic structure, where given one set of variables, the other stuff is analytic, and then vice versa, this can be a very efficient algorithm because within this picture, right, you can sort of mentally think of, imagine you could uniformly analytically draw along this direction if you hold one direction fixed, and then analytically draw along the other direction if you hold that direction fixed, and you get a very fast mixing. Right? The algorithm basically does the exact thing in one direction, then the exact thing in the next direction, and the exact thing in the original direction, and it can move very fast across the entire space. These methods are quite common in physics because there you often have this, that's also why where Gibbs comes from, right? You often have this situation that, if you know the pressure of a system, it's easy to get internal variables sampled, and then if you know all the internal variables, it's easy to sample the macroscopic variables, and so you can go back and forth. We'll encounter this situation again. In your homework, you'll encounter it. There, the task is to, there's an old, very nice example, again, by David Mackay on scientists that all have measured the same quantity but with varying error, and your goal is going to be to figure out what every individual scientist's error is and what the unknown variable is that they're all measuring. And there's a situation exactly like this where if you know what everyone's error is, it's easy to estimate what the thing is they've all measured. And if you know what they've all measured, it's easy to guess what their error has been. But jointly, the whole thing is difficult. So that's one algorithm. It's a very special case, but also a very neat one, and sometimes very useful. But if it doesn't apply, it's not useful. Yes? Yeah. So here you don't have to think about accepting, basically. It's like you just run the algorithm and you never think about accepting. You just do the iterations and you accept every single step. So this is actually what this sort of is proving, right? So if you run this algorithm, which doesn't have an acceptance probability, you just run it, then you are effectively using Metropolis-Hastings with this proposal distribution, which has acceptance rate 1. And therefore, by the proof on this slide, you are exactly sampling asymptotically from the distribution. It's still a valid Markov chain Monte Carlo method. It's not an exact sampling method from the distribution, right? It's a Markov chain Monte Carlo method, not a direct Monte Carlo method, but asymptotically produces good samples. The other method that I want to introduce today, and then there'll be more on Thursday, is a placeholder, and actually a very good one, for a way to deal with this random walk behavior, to address this, to build a method that converges better. And here, so basically the intuition is, I mean, it's kind of annoying that you have this thing, moving around here in this random walk fashion, and you kind of, in your head, you want to say something like, well, just learn that this is a smooth distribution. And when you start moving in this direction, just keep moving, go for a bit, right? Before you change your direction again, just keep moving a bit. So what we need to do is we need to give this particle that's moving around here mass, right? And make it move like a physical thing in this momentum. That's exactly the idea, and this is associated with the notion of Hamiltonian Monte Carlo, HMC, which is arguably still the base class for the efficient algorithms in this class of algorithms. It goes back to William Hamilton, Irish physicist who made major contributions to, various parts of physics. And it's actually, so it's one of these algorithms that is intimidating if you look at the math, but then if you try to be above the symbols and follow the argument, it's a bit easier to follow. So the argument goes as follows. We're interested in drawing from this distribution P, which we have up to normalization constant, and we can think of it as, well, it's a positive number, so the typical reparameterization, which is possible for almost all interesting probability distributions, is that you can think of it as the exponential of minus some function. In physics, the minus is a standard choice, and then we can think of this function as energy. High energy is things that happen rarely, low energy are things that happen a lot. Now, what we do is we actually invent a new variable, p, called the momentum, and we set it to the time derivative of x. So we're now assuming that x, our samples, are going to follow an ordinary differential equation that gives this path, that creates a differentiable path, effectively, a smooth path around. That's kind of what we want, right? We want to say, if you're moving in that direction, then keep moving for a bit. So let's get some regularity in. This is that's my computer science way of defining momentum. In physics, there would be a constant here in front called the mass. We're just assuming the mass is 1. Now, we can define a function called the Hamiltonian, which is a function of x and this new variable p, and it has the special property that we can think of it as a sum of two functions, one that depends on x and one that depends only on p. In physics, the intuition for this is that one of them is called the potential energy, something that depends on where you are, and the other one is called the kinetic energy, it depends on how fast you're moving. For example, you can set the kinetic energy to just a quadratic thing. Then we describe the dynamics of this system in terms of this differential equation. This is a pair of coupled ordinary differential equations that says the time derivative of x is equal to the derivative of this Hamiltonian with respect to p, which by this definition is just p. We just impose this, right? So the time derivative is by the definition dx dt, and we say we want this to be dh dp, and the time derivative of p, we want that to be minus dh dx. Why do we impose that? Because when we impose this, then the total time derivative, dh dt, will be 0. And then this thing will be conserved. This energy will be conserved. So in dh dx, we get a gradient of minus the energy. For those of you who are already a bit bored and want to think about, like already know how this works and want to think about other stuff, notice that this is the score of the probability distribution. Right? It's the gradient of the log probability with respect to x. Interesting. So we can think of this first intuitively as a way of imposing physics on this problem. So basically, actually, I have do I have Hamiltonian MC here? So this will produce paths within each instantiation of a particle that moves along a deterministic fashion up and down the hill, and it will sort of typically move in directions along which the probability will go up. And when it moves in directions where the probability goes down, then it slows down until it's turned around and moving again in directions where the particle moves up. Now what we'll do is we'll re-instantiate such situations over and over again, and over time we'll get these sort of smooth movements that go across the entire domain and can sort of tend to make long steps rather than getting stuck in one region. So first of all, why is this a good thing to do? And then how does it actually get implemented? So first of all, why is this a good thing to do? Because we can think of, if we run Metropolis-Hastings on this double set of variables, on both x and on p, then we're drawing from the distribution x comma p. But the distribution of x comma p, right, is some normalization constant times the exponential of minus the Hamiltonian, h of x comma p. And because the Hamiltonian has the sum structure, we're actually drawing from a product of a distribution over p and a distribution over x. And so if we throw away the p values, if we just never, like afterwards we just jettison them and only look at the samples of x, then we're drawing from the correct distribution over x. Because the marginal will be just completely independent of how we draw from p. That's nice. And kind of our goal works. We get samples from x. And there's a question? So here, what you see is every time you see this animation, that's one time step of the algorithm. So it solves a differential equation, and this chain of dots that you see is an ordinary differential equation solver running to produce a solution of the ODE until it stops. It runs for time step 1, and then it stops. And then it draws again P from a proposal distribution. So this every time one of these steps starts, there is a randomized proposal for the momentum. And so you see it sometimes moving in one direction, sometimes in another. Then it solves the ODE to time 1 and then stops again. And now the question that I haven't answered yet is, why do I get to accept this every time? Why do I not have to do some final thing to check whether I should accept or not? Because it turns out that the acceptance rate for this scheme is actually exactly 1. So actually I need to go forward 1. So it turns out that because of this is a Hamiltonian, because we've imposed this ordinary differential equation, it has the property that by its definition, by us writing down that we want the distribution to behave according to this, the time derivative of this Hamiltonian is 0. And that means that our Metropolis-Hastings Monte Carlo scheme that uses this twice enlarged state space has acceptance rate 1. And you can convince yourself that that's the case by, well, noticing that because the time derivative is 0 of h, because h is the energy of our new joint distribution, the probabilities before and after are the same, and in p space, right, in x and p space. And therefore, in this proposal rate here in the Metropolis-Hastings, everything cancels out. So at first, the typical thing that happens in your mind, I had this as well, is that you might think, what, hang on, this method always produces a sample that has the exact same probability as the one before? That sounds like it's not actually moving around in the space. It only is allowed to move on an equipotential line of the distribution. But notice that this is in this twice enlarged space. So it's in the space of both x and p. So in this visualization, there is a second dimension out of the, actually 2 extra dimensions, one out of the whiteboard and one out into the 4th dimension, where the momentum changes. And what we see here are samples where from the beginning to the end of the chain, actually, and across the chain as well, the joint probability always stays the same, but the system is moving around. Sometimes it's moving energy into x, into the potential, and sometimes it's moving energy into kinetic energy. And in such a fashion that the total energy always stays the same, but sometimes you end up being faster and sometimes you end up being slower, such that marginally those samples are all actual samples from the distribution if you run the chain for long enough. And to do that, you have to solve an ordinary differential equation. So you have to write down an ODE solver. And I used to have slides where I told people how to solve ordinary differential equations. But now we don't have to do this anymore because you now know that ODE solvers are, just Kalman filters. So here is a Kalman filter basically written down in a fancy fashion. But we don't need to do that anymore. I also can show you code, but it's Hoynes method. But, it's just a Kalman filter. So, yes? Yes. Okay, so this is really like a crucial point. So let me take 2 minutes to explain this again. So remember when we did the definition. So there's basically 2 ways of thinking about this. But it always boils down to the following step. We introduce this new variable p. We call it x dot. And now we say when the algorithm runs, so within one of these steps here, within one of this, like producing one of these black lines, what we'll do is we solve an ordinary differential equation that says simultaneously simulate x dot and p dot. You can think of these as a state space of a Kalman filter with 2 states, right? X and p, such that x dot p dot is given by p comma minus gradient of the energy with respect to x. So p comma score of the probability distribution. When we do that, then that means that x dot is equal to the hdp and p dot is equal to minus the hdx by the way we've defined it. And that then means that the hdp, capital H, where H is this new energy, the Hamiltonian, dt is by definition of chain rule the hdx dx dt plus the hdp dp dt. We have defined what the hdx is, what the xdt is, namely the hdp, and we've defined what the pdt is, also p dot, which is the hdx. Now this cancels, everything is 0 because they commute. And that means the time derivative of h is 0, and therefore our acceptance rate will be 1. Under the assumption that we're actually able to solve the ODE. If you're using an approximate method to solve the ODE, it doesn't always perfectly work, which is why this code actually has a check here at the end where we compute the Hamiltonian and you sort of do an assert to check whether you've actually correctly simulated or not.
Is that then why we saw some of the samples get rejected in the continuation?
I think they don't get rejected actually. I think do they? Yeah, so there's these green lines at the end where it actually checks. Okay, yeah, occasionally there's a red line, yes, and then the okay, interesting, yeah, I didn't even see this, you're right. So when there's a red line and it doesn't get accepted, then it's because the ODE solver was bad and didn't manage to actually correctly solve. So for a long time, this is a very smart idea that gives you very high acceptance rates. And now the only thing left to do is some engineering, effectively. So one thing you noticed, I can show you, if we solve for a pretty long time, then what you often see is that this ODE goes basically back and forth across the entire domain. Sometimes you walk, you're in one corner of the problem, and then you take a long walk. You invest so much compute to go all the way to the end, and then it turns around and walks backwards again. And that's quite wasteful, right? We sort of, just to make a small step, we had to simulate these dynamics for a long time. And so you want to avoid that, so you want to find some way of adapting the parameters of this algorithm such that it doesn't do this, basically, but still remains a valid Markov chain Monte Carlo method. And that's actually an idea that was proposed by, or that's an idea behind one algorithm that tries to address this that became quite popular by Matt Hoffman and Andrew Gellman, published in 2014, called the no U-turn sampler, the NUTS no U-turn sampler. And that became a thing for, where is it actually? Native NUTS. I'm not going to tell you how exactly this algorithm works, but you can imagine what it does. It actually produces two solutions in opposite directions. So it solves an ODE forward and backward in time, produces two of these proposals, checks for when they stop moving away from each other and start turning towards each other, and then randomly chooses one of them. And then one can show that this is actually still a valid Markov chain Monte Carlo method. It still satisfies detailed balance, and everything is fine. And now you have a very efficient method. So such algorithms, and with that I'm basically at the end, such algorithms became, and now we're getting back to like a bit of history, became very central to a field, a subdomain of statistics and machine learning called probabilistic programming, which, well, okay, so I'm trying to not be too critical, but which had its heyday in like the decade from like 2010 to 2020 maybe, where the idea was, oh, maybe we can write programming languages where you get to define a joint probability distribution. So instead of instantiating variables that are integers or floats, or arrays of integers or floats, we're going to create variables that are instances of a Gaussian or a gamma distributed random variable. And then we can write programs in the way that we are used to in, with a Turing machine. You can write x comes from a Gaussian, y comes from a Gaussian. And now I'm interested in the variable z, which is x times y. And now I'm going to evaluate a z, and I will condition that on the fact that z has the value 5, because I've seen that. And now there has to be some magic happening in the background in my computer that then tells me what x and y are, that computes the posterior of x and y. This is the idea of probabilistic programming. There are variants of this that are basically always implementing Bayesian inference on programs that can be written in the form of a Turing complete language. There's actually several programming languages for this purpose that have been invented and built over the year. Some famous ones include Church, for example, named after Alonzo Church. And there's a variant of Clojure. There's something called Anglican as a variant of Church, right? And there are also frameworks that aren't based on Markov chain Monte Carlo methods, but on variational inference. Microsoft had a toolbox called infer.net. They still exist. If you go to probabilisticprogramming.org, you can find a long list of such programming languages. And the majority of them are basically wrappers around such Markov chain Monte Carlo methods, where you get to write down a program in a programming language, and then instead of instantiating variables as floats and integers with exact values, you instantiate them to be draws from a probability distribution. It's still a very powerful idea for some forms of, for example, scientific inference. And well, I think that will have to be enough to tell you about how these algorithms work in the background. Oh, Pyro, for example, is also one that might be quite interesting for you to look at. Written by folks at Meta, I think. Well, no, sorry, at Uber some time ago. But I get a sense that in like the last few years, a new way of thinking about how to draw samples from a distribution based on samples is emerging. And that's the idea of generative methods that draw from pretty much general probability distributions by initializing from some basic some basic probability distribution and then transforming the samples to look like empirical samples, diffusion models, for example, and flow-based methods. And that's what we'll talk about on Thursday as an end cap on the random number section. For now, please give feedback, and then I'll see you on Thursday.